Welcome everybody, and thank you for coming. This is how my DIY RFID reader became a lifesaver. In this talk, we're going to cover how you can build your own RFID reader from base components, and a little bit about some quirks in the design of RFID tags that are used to track your pets. Before we get into the actual technology of it, I'll tell you a little bit about myself. I go by Dozer. By day, I'm a penetration tester and exploit developer. And by night, I'm still an exploit developer and an electronics hobbyist. I'd like to emphasize that I am not an electrical engineer, so everything that I'm about to say about electronics should be taken with a grain of salt, because I'm just trained off of the internet. Before we jump into the electronics, I want to give you a little bit of background on why I built this thing in the first place. That is because I have these cats, named Huntress Wizard and Cinnamon Bun. These cats have a litter box, of course, and that litter box is behind a door. Now, I want to keep that door closed for aesthetic reasons while still allowing the cats access to the door, or to the litter box. And because I'm an engineer, I came up with the most overcomplicated design possible to solve this problem. The plan being to detect the presence of a cat via its implanted RFID tag and then open the door with a linear actuator or something similar. Unfortunately, I'm going to have to spoil for you that this plan did not work. And that's down to really two problems. The first being that RFID is really short range, and this might be overcome with a big enough reader, which kind of goes against my aesthetics plan. But the second problem is the bigger one, and that's that training cats to do anything is difficult. If any of you own cats, you know that they will sooner do anything other than the thing that you want them to do. I, of course, ignored these problems and carried on with the build anyway. So this is the sort of RFID tag that we're trying to read. It consists of a glass capsule that is usually implanted underneath the skin, usually between the shoulder blades. And inside of that is an antenna coil and an integrated circuit with some non-volatile memory and some logic circuitry to transmit the contents of that memory back to a reader. In order to read these tags, we need to provide it with a power source, a clock signal, and a communication channel back to the reader. All three of these things can be provided pretty elegantly by a coil in the reader itself. To power the tags, all we have to do is run an alternating current through the coil in the reader. This will produce an alternating magnetic field, and when the tag enters that field, it induces a current in the coil in the tag, which powers up the tag and makes it start transmitting data. Seeing as we're using alternating current, we basically get the clock signal for free. All we have to do is alternate current at a fixed frequency. In the case of these tags, they expect to be driven with a frequency of 134.2 kilohertz. And the communication channel aspect is a little more complicated, so we're going to look at that in line with the rest of the design of the reader. The brains of our reader is going to be an off-the-shelf Arduino Nano. And in order to drive the coil, we're going to use one of its PWM pins. Now, we can't hit the desired frequency perfectly because of the limitations of the 16-bit timer in the Arduino, but we get pretty darn close to it, close enough to make it work, and as I've learned from this project, a lot of things in analog electronics appear to operate under the principle of good enough. So the rest of the reader, we take the signal from the PWM pin and pump it into a push-pull amplifier. The amplifier isn't strictly necessary to make everything work, but what it lets us do is draw as much current as we want without having to worry about the current limitations of the Arduino's GPIO pins. The Arduino can only supply around 20 milliamps per GPIO pin, and I wasn't sure how much current I was going to draw, so we put a push-pull amplifier in there first. The amplifier then drives the coil at the frequency that we just described. On its own, this coil is not yet capable of receiving data from a tag. In order to do that, we need to make the coil resonate at the frequency that we're driving it at. Resonance is a little bit outside of the scope of this talk, but what you can think of it as is like pushing someone on a swing. You tend to time your pushes to match the natural period that the swing wants to swing at. Now, we need to flip that concept on its head a little bit because we want to drive the coil at a predetermined frequency. This would be like having to change the length of the chains on a swing to make it want to oscillate at the frequency we want to push it. And to do this electronically, we add a capacitor between the coil and ground. This lets us tune the frequency of the coil, the resonant frequency of the coil, to anything we want according to this frequency, and we just have to add the right amount of capacitance. Doing this sets up a very delicate balance that is easy to disrupt, and this disruption is how the RFID tags communicate with the reader. When a tag is present and it wants to modulate data into the reader's carrier frequency, it does this by adding and removing an additional load to the tag's coil, which causes it to draw more or less current and causes the waveform to collapse every time it adds that additional load. This is a method known as amplitude shift keying. You can think of it like AM radio, but for digital data instead of analog data. So our next job is going to be to try to recover this square wave out of this messy carrier wave. In order to do that, we need to know the frequency of the data that's being transmitted to us, and to get that information, we need to look at the encoding. The tags transmit data using differential Manchester encoding, and transmits 1 bit every 32 cycles of this carrier wave. Additionally, because of the way differential Manchester works, a 0 is indicated by a state change in the middle of a bit period, which means our signal can change twice as fast as this 32 cycles, giving us a data frequency of about 8.4 kilohertz. Now we're going to use this number in a lot of places to do some signal processing and some decoding later on. The first stage of this signal processing is we're going to feed the signal through an envelope detector. This consists of a diode which just rectifies the signal, converting it from AC into DC, and then into an RC filter, the purpose of which is to try to smooth over the peaks and troughs of our signal, turning it into more of a square wave. In order to do that, we need to choose a time period over which to smooth out the signal. This needs to be between the frequency of our data signal and the frequency of the carrier wave. On the suggestion of someone on the internet, I chose a time period that is 1/10 of the data signal's frequency. This seems to work well enough. All we have to do is choose electrical component values that provide the smoothing over this time scale. The output of our envelope detector gives us this. Now this is starting to approximate a square wave, but we still have a lot of high frequency noise in the signal from the carrier frequency. And we need to remove that, and we can do that with a low pass filter. As the name suggests, a low pass filter allows low frequency signals, like our data signal, to pass through it while suppressing the higher frequency signals of our carrier wave. We need to choose a cutoff point at which we want higher frequency signals to be suppressed and the lower frequencies through. We need to choose this to be a frequency at or slightly above the frequency of our data. And again, we just choose electrical components that give us that cutoff point. The output of the low pass filter gives us this. It slightly distorts the square wave, but what we gain is a clear distinction between a low and a high state. If you look at the red line on the graph, you can see that it pretty neatly divides the signal into low and high. Now all we have to do is clean this signal up, and we can do that by amplifying it up to the logic levels of the Arduino, and we can do that with a couple of op amps. These op amps are set up in an inverting configuration. That means when the input signal is low, it drives the output high, and when the input is high, it drives the output low. We need to tell the op amps what it should consider high and low, and I've done that with a simple voltage divider. This is set at about 3 volts. Anything above 3 volts, the op amps will consider to be high. The specific set point of this voltage divider doesn't matter too much because we're going to run our signal through a series capacitor, which causes the signal to oscillate around the set point of the op amps. The output of our amplification stage gives us this. This is a nice clean square wave that is suitable to be fed back into the Arduino for further processing. And we're going to feed it into one of the Arduino's interrupt pins so that we can capture the time between each state change of the pin, because we still need to undo that differential Manchester encoding. So this gives us the time periods between each state change. We can further process this down by dividing it by half of the bit period to normalize the data, into something that's a little bit easier to work with. This normalized data is then decoded by looking for either pairs of ones or a two. If we see a pair of ones together, that means that there was a state change, half a bit period occurred, another state change, half a bit period occurred, and a state change, which in differential Manchester indicates a 0. If we see a 2, then there was a state change, 2 half-bit periods, and then another state change, which differential Manchester considers a 1. If we see any other value in this array, or a 1 that isn't paired up with another 1, then we know we've received some sort of bad data, and we can throw it all away and start over. The nice thing about this is it gives us a bit stream that's continuously flying in, and from that we can try to parse some meaningful data. Parsing is pretty straightforward because the structure of the data inside of these tags is really conducive to parsing. Someone paid attention while they were building this. The data always starts with an 11-bit header. This header consists of 10 zeros followed by a 1, and it should be impossible for this number to appear anywhere else in the data. So, excuse me. As the data is streaming in, we can just look for this header value, and as soon as we see it, we know we're locked on to the start of the tag's data and can start parsing the rest of it. All of the following data is broken down into bytes, and each byte is followed by a binary 1 as a sort of a control bit. This makes it so that we can make sure we haven't lost track of our place in the signal. If we read a byte and it's followed by a 0, then we know that something has gone wrong, and once again we just discard all the data and start over. We'll catch the tag's data the next time it transmits it. The next 6 bytes are the 15-digit unique identifier for your pet. This is what you would normally see displayed on an RFID reader, and it's the number that you load into a database so that when your pet gets lost, they can be returned to you. Following that is 2 bytes worth of flags, most of which are reserved for future reuse. The ones that are defined tell us if there's extra data at the end of the tag, and if this tag is intended for animal use or not. Following the flags, we have a CRC checksum of all of the previous data, not including the header and the control bits. And following the checksum is the extra data segment, which may or may not be present based on the status of one of the flags. And really, that's all there is to the signal parsing, signal processing and digital parsing of the tag data. So for you, I have a demo prepared here. I have the circuit that we described set up on a breadboard. And if you give me a second, I will switch over to the Arduino input. There we go. Just a serial port. I also have a bare RFID tag. It's probably impossible for any of you to see because these things are only about 7 millimeters long. Copper coil of the reader, and if I bring the two close enough together, there it goes. It starts dumping out data continuously. One more other thing, apart from the demo, I also have a circuit simulation of the entire reader. This is available on the GitHub page if any of you want to play with it. Well, I just broke it. That's fine. It's fine. It won't be broken on GitHub. This will let you play with some of the values, and you can watch how the signal changes over time. Maybe you can find a better design than I can because, again, I'm not an electrical engineer. So let me jump back into the presentation here. So we've covered how the reader works at a hardware and software level, but we haven't covered how this thing became a lifesaver to me. So you just saw this thing work with the bare RFID tags that I bought off the internet, and after I developed it, I tested it out on the cats. And it appeared to work. After all, it printed out a number, just like the other tags did. But what I didn't expect is when I compared that number against the number that they're registered with in the database, one of the cats had a 1-digit off by 1 error in the number that was in the database. This had me pretty confused for a little while. I thought for sure that there was just something wrong with the reader that I had built. After all, I built it out of stuff that I just had laying around. But I went over it with a fine-tooth comb at the hardware and software level, couldn't find a single thing wrong with it. You saw how the data is structured. It's CRC checksummed. It's basically impossible for this thing to output a wrong value, which led me to the only remaining conclusion that the number in the database was wrong. And this is really the reason why I wanted to give this talk in the first place. Because if my cat had run away before I had found and corrected this error, she probably never would have been returned to me. And this made me dig into the problem a little bit more, which led me to finding some statistics. Evidently, about 40% of pets with microchips are unregistered. That is, a lost pet is found, they scan the chip in the pet, they look it up in the database, and no record comes back. The natural assumption here is always that the pet owner forgot or was too lazy to register the number in the database. But now we know for absolute certainty that some portion of these pets have to be the result of someone inputting the wrong number into the database, not someone forgetting to put it in at all, which I really find to be unacceptable considering the technology here. After all, we all know that people make mistakes, and as designers, we should try our best to compensate for these errors in our devices. It did a great job. The data is checksummed, but when the reader reads the data, it displays a number and throws the checksum away. Had that checksum been included as an integral part of the ID, or if the ID had parity bits inside of it instead of being an ordinary integer, then these problems could have been detected or maybe even corrected when someone tried to put the information into the database. Unfortunately, it's a little too late to fix this particular RFID protocol. It's too widely spread. I don't think we'll ever see a fix for this. But what it's not too late for is for all of you out there who are working on who knows what to make sure that all of your data is properly parity bitted and checksummed and all of that, especially if you're expecting the data for whatever you're producing to go through the hands of a human. Someone will screw it up at some point, and we need to compensate for this. On top of that, I'm sure some of you out there are pet owners, and there's really no other fix for this other than to get your pet's chip checked. Hard sentence to say. And there's actually a sort of national holiday for this called Check the Chip Day. Check the Chip Day focuses more on making sure that your contact details in the database are up to date and that the chip is functioning at all. But I would like to encourage you to also get the number from the chip when someone goes to read it and verify that it matches the number in the database. You don't even have to build my janky device to do that. If you own a flipper, sometime after I built this, they updated the firmware to support reading these FDX-B chips, so you can check it yourself. If a flipper isn't an option for you, then you can just ask your vet. That's what I did because I didn't have 100% faith in this device. So the next time I brought my cat in for a checkup, I had the vet break out the reader, read the chip, show me the number, and I was able to confirm that, yes, the number in the database was wrong, which led to a very confused vet who wondered how I knew there was a problem in the first place. And that's really all I have for you. You can find the source code and designs and more than this presentation contains on the GitHub page for this project. Also, you can check out my YouTube channel to see other crazy things that I've done. Does anyone have any questions? Yes, you. Yes, those are both my cats. Yes. Yeah, I'm unclear on the purpose of the animal use flag. I don't know why someone would be using this particular protocol for non-animal use. My understanding is that it was designed specifically for animal use. Oh, speaking of chips in humans, I'm unclear on whether or not this will read the chips that some people choose to get implanted in their hands. My understanding is those run at a higher frequency, up in the megahertz, that I don't think this is compatible with. If you don't care about reading your pet's microchip, this could also be slightly retooled to read certain RFID fobs, the sort that you might use to get into an apartment. They run at a very similar frequency. I think they use 125 kilohertz amplitude shift keying, and I don't know a thing about how their data is actually stored. Anyone else? No, looks like that's it. Thank you.